Hi everyone, this is a recording of Lab 2 for ENL 270 on Opamp Introduction. So this lab is looking at how we can use op-amps in basic applications. You'll note here on the first couple of pages, there are some of the properties of the op-amp we are using given. There's the LMC6462. The key properties are given down here, which we talked about in lectures. And there are a few questions relating to these key properties here for you to fill out. There is also a diagram, a pinout as we call it, of the op-amp package we're using. So you can see there are actually two op-amps inside this chip, and there's 8 pins that are labeled starting from 1 to 8. The actual chip we're using looks like this. Is a small black chip on here. And you can see there's a notch cut into one side. That notch indicates where pin 1 is. So if you compare that to this diagram here, you'll see this shows both the notch and a little dot here indicating where pin 1 is. Similarly, on the op-amp itself, you can see the notch and a small dot indicating pin 1. All IC chips, integrated circuit chips, will have some indication on them of where pin 1 is. That way you can know when you're wiring up what pin you are connecting to. We, in this lab, are going to be wiring our op-amps onto a breadboard, such as this one. There is, at each desk, a red lab manual, which has some information inside it, including notes on the layout of a breadboard. So for these breadboards, you'll notice there are 2 center sections here with a division down the middle, and a top section and a bottom section. The top and bottom sections are generally used for power, for supplying power. They are connected continuously across the breadboard, so going from one end to the other horizontally. And they are separate from each other vertically. So this top line here is separate from this bottom, the row below it. That way we could supply 10 volt to that top row and have ground on the row below it. And that makes it easy to access those power rails from anywhere inside the breadboard. The internals of the breadboard are wired around the other way. The columns are continuous within one section. The rows are not connected. So these are connected going down. So for example, this column labeled column 15 is continuous down until this cut in the breadboard here. The column 15 on the other end is also continuous, but not across this cut. There is a division here. The idea of this division is that we can then take a package like this op-amp, what we call a dual inline package, or DIP, and put its pins on either side of this cut. That way these pins are not shorted together. The top and bottom pins of the op-amp are not connected. For this lab, we have already wired up the power connections for this op-amp. So this is the positive power supply, the negative power supply here. One important thing to note for this op-amp especially is that it is limited to plus and minus 5 volt supply rails. So whenever you're using an op-amp, you need to check carefully what the required and maximum supply voltages are. Okay. That means when we're setting up our power supply, that means we need to set these to 5 volts. And remember, this is an operational amplifier. We need a dual supply for this. So positive and negative 5 volts in this case. So I'm going to set up the power supply now. So I'm going to set these both to 5 volts. And leave the current limit at 100 milliamps, which will be more than enough for what we're doing in these labs. Remember from the previous labs how we wire up a dual supply. We pick one of these adjustable supplies to be our positive voltage, the other to be our negative supply. Again, it doesn't matter which one we pick for each job. We just need to be consistent. So I'm going to arbitrarily pick the left-hand one as the positive 5 volt supply. I'm then going to connect a banana to banana wire to it. And I'm going to connect that to the positive terminal of the supply. I will then connect that into the positive terminal on the breadboard. This terminal here, you notice these are color-coded. Color coding is a convention, it's not a rule, but it is a very useful convention. It is worth following as if it were a rule. So that is going to be our positive 5 volt supply to the breadboard. Similarly, we are going to supply -5 volts from this other supply here. I'm going to use another banana to banana cable. And I'm going to connect that to the negative output, to the negative supply here. So not to the positive one, but to the negative one. And I'll connect that into the negative supply on the breadboard, which is this central black one here. The last thing we need to do is to make sure these have a common ground reference, so that they are +/- 5 volts with respect to some shared ground. Remember that we do that by connecting the earth terminal on the far side of the power supply into one of the unused terminals. In this case, I'm going to use the positive terminal of our negative supply. And we connect the unused terminals together such that they are shorted together to have a single ground. So I'm going to take this one here, and I'm going to jump together the negative output of the +5 volt supply. I'm going to connect that to the positive output of the -5 volt supply. Those are both connected to this common earth reference, so now they share a common ground connection. We also want to supply that to our breadboard in case we need a ground connection at all in there, which I'm going to do using one more banana to banana cable. I'm going to plug one end into the earth reference here, because we're using that as our ground, and the other one into the ground reference on the breadboard, which is this green terminal here. So now we have our power connection set up for our breadboard. They are connected up with ±5 volts and no more than 5 volts for these op amps, and 100 milliamp current limit. While we're setting the equipment up, it's also worth setting up your oscilloscope as well, because you're probably going to be using that. I have already checked the compensation on these probes, if you remember that from lab 0. You can see, for example, on channel 2, I have a nice square wave at 1 kilohertz and 2.51 volts peak to peak, which is the standard reference signal on these oscilloscopes. Remember that it may be different on other oscilloscopes. You will need to check the manual. It is worth doing this every time you go to use your oscilloscopes, just to make sure everything is set up correctly. And I've already adjusted these so that they are nicely compensated. Okay. The first circuit we are going to build is this basic comparator circuit. So a DC comparator with no feedback. For that, we are going to need a single op amp with ±5 volt supplies, which we now have set up here. And we are going to need a ±5 volt supply for input and 3 10 kilo ohm resistors. So I have 3 10 kilo ohm resistors here. If we wanted to, we could measure the resistance of these as well to check that they are 10 kilo ohms and check how accurate they are. So it's always worth doing that just to be sure that they are what you expect. In that red folder I showed you earlier, there is, amongst other things, a resistor color code chart in there as well, if you wish to use the color codes on the resistors and refer to this chart. Okay, this circuit requires us to have +5 volts going through one of the 10 kilo ohm resistors, and that then goes into the non-inverting terminal of one of the op amps, and parallel to that, 2 more 10 kilo ohm resistors, both in series with each other, going down to the -5 volt supply. The way I'm going to do this is I'm going to connect one of these resistors into the 5 volt supply, which I'm also using to power the op amp, and connect that into one of the non-inverting inputs. If we refer back to our pinout diagram, we can see that pins 3 and 5 are some non-inverting inputs we can use. It doesn't matter whether we pick package A or B, it doesn't matter which op amp we use, provided we pick one and stick with it. So you can't mix and match pins from between them. So I am going to use pin 5 of op amp B just because it's more convenient for me to use here. Pin 5 is the top right corner. So I'm going to take one of the 10 kilo ohm resistors and connect it between the top right corner of the op amp and my 5 volt supply connection. So the wires of this resistor push into the holes on the breadboard. Remember that in the central part here, the columns are connected. So to connect to pin 5 of the op amp, I connect the resistor in the same column as pin 5. And I connect the other end of that into the 5-volt supply rail along the top. When you push in, make sure they're in nicely, but don't overdo it. You shouldn't need to shove them in. If you do, they can bend again away a bit, and sometimes the leads can bend underneath the breadboard and start shorting things out unexpectedly. So you don't need to force things into it. Okay, that is one of the resistors I need. We also need those other two between the non-inverting input and ground. So these two here. These go from non-inverting input to -5 volts. So I'm going to take my other two 10 kilo ohm resistors, and I'm also going to connect one of them into the non-inverting input of the op-amp I have chosen, so pin 5 in this case. So I'm going to connect one of them into the same connection as the other resistor. The other leg of this resistor, I'm going to just connect up somewhere else on the breadboard for now. It doesn't really matter where, provided it's out of the way, it's not shorting or connected to anything it shouldn't be, and that it's neat and tidy. You'll see this as we go on in future labs, but it is worth taking time to make sure breadboard layout is neat and tidy. It will save you a lot of trouble in the future. So that's one of our 10 kilo ohm resistors. That is this connection here from VI plus to this 10 kilo ohm. We then want to put that in series with the other 10 kilo ohm resistors and have that go to -5 volts. To do that, I'm going to take my final resistor and connect one end of it to this 10 kilo ohm resistor here, which I've jumped off to a spare spot in the breadboard. And the other leg I will connect into the -5 volt supply rail on the bottom. So now I have constructed that circuit with those resistors. I have my plus and minus 5 volt supplies for the operational amplifier. I also need to connect the inverting terminal of this op amp to ground. To do that, I'm going to grab a piece of wire, what we would generally call a jumper, and I'm going to use that to connect that pin to ground. You can choose jumpers of any length really, and any color you want. Again, it's worth, if you can, sticking to some sort of color code convention and using jumpers that aren't too long or too short. If they're too short, it's going to be really difficult to connect things up. If they're too long, they'll get in the way, and they can act as antennae and bring in interference and other signals into your breadboard, which might make things read incorrectly or operate strangely. So I'm going to grab a jumper wire here. I know from the pinout reference I have in the lab manual that the inverting terminal rather, is pin 6. I want to connect that to ground. So I take the jumper, I put one end of it into the same column as pin 6, and it can go anywhere in that column, wherever is convenient. And the other end I will connect to ground, like so. So it's this wire here. So one end is the same column as pin 6. The other end is in my ground row along the bottom here. So I have this set up so I've got ground at the top of this bottom section and -5 volts as the bottom row. Now our circuit is constructed. Once we're happy with our circuit, we can turn it on and start seeing what it does. So in this lab, we've asked you to first of all calculate what the theoretical output of the op amp should be based upon the circuit we've set up. And we've also got enough information to determine the threshold voltage for this comparator. Remember that a comparator takes an input, which could be fixed or varying, and compares it with another fixed reference. It can be inverting or non-inverting, as we've talked about in lectures, but one of these terminals, the inverting or non-inverting input, is fixed. The other one is either fixed or variable. That's up to us as designers. Okay, next what we are going to do is we are going to measure the output voltage from this circuit. The way to do that is we need to use one of our oscilloscope probes and connect that between the probe end to the output voltage of this op amp. The other end we need to connect to ground. There are a few different ways you could go about doing this. The neatest way is to use jumpers to easily connect the op amp probes into the breadboard. You might be tempted to use the legs of components like resistors and hook onto those. Don't do that. That will often leave those out of the board without you realizing and break your circuits. It's also very difficult to then probe different points and see what's going on, and it's just very messy. Instead, grab a reasonably short jumper and use that to connect in. So I am going to grab a couple of jumpers here. I'm going to connect one of them to my ground lead of my oscilloscope. The other end I'll stick into my ground rail. I will then connect the other leads, my other jumpers, to the probe hook on the oscilloscope. And I want to connect the other end of this jumper into the output pin of this op-amp. Looking at our diagram again, we're using op-amp B. The output of that one is pin 7. So we can connect our jumper into pin 7 of the op-amp. Again, on the breadboard, that is anywhere along the same column as pin 7. So I've connected it up like this. At the moment, if we were to try and measure things on our oscilloscope, we wouldn't get anything reasonable because our circuit is not powered. So the last thing we need to do is to turn on power to our circuit. So we need to enable the outputs of our plus and minus 5 volt supplies. I'm going to turn this on now. When you do that, it's worth checking that you don't get one of these lights coming on. These lights here have a little CC label next to them. And this, if they come on, that indicates that the power supply on that particular side has hit a current limit. So remember, we set these to a 100 milliamp current limit. If that light were to come on, that would mean we are drawing that 100 milliamps and in fact trying to draw more, and you'll probably see the voltage will drop. That's usually a good sign that you have a short circuit in your circuit. So at that point, you should turn the power off and check your circuit to make sure you've constructed it correctly. Okay, you can see in this case, it's working fine. I have no current limit issues. If I then set up my oscilloscope to measure it, I'm just going to press auto scale. You'll see it turns both channels on. Because we are measuring what is a DC output, the oscilloscope will tend to turn everything on as it doesn't have a strong signal to measure, or a strong variable signal to measure. So I'm going to turn channel 2 off, and I'm going to manually adjust the scale on channel 1. So I'm going to change this time scale. At the moment, this has a time scale of 10 microseconds per horizontal division, which is quite fast. And so that's going to pick up a lot of very small variation and noise, which you can see is this flickering here. What I'm going to do is use this horizontal dial at the top to change that time scale. We don't need to be at such a short time span. So I'm going to dial that out. Something like 10 milliseconds per division. We're also at a vertical scale currently of 100 millivolts per horizontal division. And again, that's a lot more sensitive than we need to be for this measurement. So we'll pick up a lot of noise, which isn't really as significant as it looks here. So I'm going to use this dial above channel 1, the large dial, to change that scale. So I'm going to turn that down to about 1 volt per division. I can see my signal has dropped off the bottom of the screen now. To move it up, I use this small dial here below channel 1, because I'm using channel 1, and I can move this up. You'll notice on the left-hand side here, there are a couple of marks. This one at the bottom here with a little 1 and a ground symbol indicates the 0 or ground reference for this channel. The T here next to the signal indicates where the mean or the average of that is. For this DC signal, it's just in the same line as the signal. So we can observe this. There's 2 ways we can measure this voltage. One is we could say, well, we're at 1 volt per division. If we count up, we go 1, 2, 3, 4, 5 volts. So we're getting 5 volts out of the circuit. We can also measure the voltage out of the circuit using the measurement tools on the oscilloscope. Note that if you measure the peak-to-peak voltage, you'll get something quite small. That's because this signal is, if it's a DC signal, should be pretty constant. It shouldn't be varying. Therefore, should be little to no peak-to-peak variation. So to measure that accurately, we could use the measurement menu, selecting channel 1. Instead of peak-to-peak measurement, we could use something like the maximum or the minimum or the top or the DC RMS across the full screen or the average across the full screen, whatever seems appropriate. which one you use some will depend upon what you're doing in practice. In this case, it won't matter too much. So I'm going to take the full screen average of this channel, and I get pretty much 5 volts, 4.98 volts. Okay, so that is our comparator set up and working as expected. The next question asks us to grab a fourth 10 kilo ohm resistor and to touch the leads of that resistor such that we form this little circuit down here. So we're going to put a 10 kilo ohm resistor in parallel with these other two 10 kilo ohm resistors. We can then calculate what we expect the voltage at this input here to be, and therefore what we expect the output voltage to be. So you should go ahead and calculate that first, then you can test that. So I have one more 10 kilo ohm resistor here. I'm going to touch that across the leads of these two lower resistors here, which are forming that 10K in series of 10K network. I'm going to touch them across to create a parallel connection. If I do that, you'll notice that as soon as I do that, the output voltage changes. If I wire this in properly so I can show you what's happening, you can see the output voltage has changed. Now in this case, you might be tempted to say it's gone off the screen, hit auto scale. We can do that. If we do that, because again, we have a DC signal, we'll have to then turn off channel 2 and do a whole bunch of rescaling anyway. So what I'm going to do is in fact actually shift channel 1 up and up and up till I can find it. So now I see that channel 1 has a voltage that is below the ground reference and is in fact 5 volts below. So this is negative 5 volts output now. Hopefully that makes sense considering what you calculated for the input voltage with that resistor in parallel. Okay, so that is section 2.3 on the basic comparator. What we are going to do now is change our circuit to be this circuit so that we have a comparator with an AC input. So I'm going to deconstruct the circuit I have here and then construct this circuit as shown here. Again, we only need one op amp for the circuit. For simplicity's sake, I'm going to use the one I've already been using. So I have disassembled the circuit from before, and I have two 10 kilo ohm resistors, one coming from positive 5 volts to the non-inverting input of one of the op amps. In this case, I'm using package B. The other going from the non-inverting input to negative 5 volts. So forming our comparator threshold. On the other input, we want a sine wave. There are two ways we can set up the sine wave. We can use our function generator as we did in lab 0. There is also a wave generator on the oscilloscope. You can use either. For this lab, I'll use the function generator again. In future labs, I will also use the wave generator on the oscilloscope to show you both options. So we want a sine wave with particular specifications. We want a sine wave input, so a sine wave signal, just selected on the function generator here. We want it at 100 kilohertz. So I'm going to change my frequency to 100 hertz rather, sorry. So we want to select a frequency in the hundreds of hertz range. And we want 100 hertz. So move the dial up until I get to 100 hertz. Okay. We want to have 4 volts peak to peak. So I'm going to set the peak to peak voltage to 4 volts. Currently, it is at 1 volt peak to peak. If I dial up the amplitude, you'll notice I'm limited to 2.14 volts. So I need to turn the attenuation a bit lower. We can turn it off. In this case, I'm going to turn it off completely. And then I can dial this to 4 volts or near enough too. And finally, we want to have 0 offset. So we want no DC offset at all. If I press the offset button on the front here to check that, I see we're at 0 volts of offset. So this is the signal we want to generate. To connect that into our circuit, we are going to use a BNC to alligator probe connection, like this one. So the BNC connection end goes into the function generator. Remember, the output we're using is the far right-hand side one, the 50 ohms output. So I connect that in, push and twist. The crocodile clips are used to connect into the circuit. The red is the positive voltage, the black is the ground reference. To connect these into the circuit, I'm going to use jumpers. So these are nice, neat connections. I'm going to take one for the positive connection. I'll hook the crocodile clip onto one end of it and plug the other end into the circuit. And the same for the ground reference. I'll hook one end of the jumper onto the black alligator clip and the other end goes into ground. So we have 5 volts or 4 volts peak to peak with respect to ground. Finally, we want the input sine wave voltage to go directly into the inverting terminal of this op-amp. Remember from our pinout diagram, the inverting terminal is pin 6 on the package B that I'm using. So I plug in this end of the input signal into the inverting voltage pin of the op-amp I'm using, which is pin 6. Cool. That circuit is now set up. What we want to do is measure both the input and output voltage with the oscilloscope probes. So we're using one probe before, we're now going to use both probes at once. So for my second probe, I'm also going to want to put some jumpers on that so that I can place it in the circuit nice and easily. So I grab another couple of jumpers and hook them onto the other oscilloscope probe. I want to use one probe to measure the input and the other to measure the output. It doesn't matter which probe I use for which. It's up to you. Generally, for no good reason, I tend to use probe 1 for the input, probe 2 for the output. It's up to you. It doesn't really matter, provided you know which channel is measuring what. So it doesn't matter, but make sure you do know which way around they are. In this example, I'm going to use channel 1, which remember is yellow, to measure the input voltage. So I put the ground end of the probe into my ground reference, and the probe sent end goes into where I'm placing the input signal in. I could direct that connectly to the crocodile clip this is coming through, but that's a bit messy and prone for error. Instead, I'm going to also plug this into the breadboard in the same column of the breadboard as to where I'm supplying that voltage. So I do that. You'll see I'm getting a bit of a sine wave signal. It's a bit messy, so I'm going to press auto scale. And you see we're getting a somewhat messy sine wave. So you might be thinking what's going on at this point. Here it's worth checking your connections. You'll notice that I haven't yet turned the op-amp on either. The power supplies are off, so that may also have something to do with it. I'm then going to connect channel 2 up to the output signal of the oscilloscope. Remember the output signal of the op-amp. Remember on this op-amp, pin 7 is our output. So again, the ground probe goes to ground, and the probe itself goes into pin 7 using the jumper. So my circuit currently looks like this. So you can see, even with a bit of care, they can get quite complicated and start to get a bit messy. It's worth taking your time to lay them out nicely so you know where everything is. Otherwise, you will come across problems. Finally, I'm going to turn my supply to the op-amp on. You can see immediately that the weird distortion I was having on channel 1 has gone away. That was due to the fact that the op-amp wasn't powered. And so when that comparator network was set up, there was no voltage there, and so everything was floating around a bit weirdly. You can see channel 2, which is in green, you might be able to see it's gone off the screen, looks a bit like a stretched out square wave. I'm going to press auto scale to fix that scaling. And now you can see our input at channel 1 and our output at channel 2. The first question here is asking about the phase of the output voltage with respect to the input voltage, whether they are in or out of phase and why it's like that. To make that a bit easier to see, I will move channel 2 up a bit So you can see whether it is in or out of phase with channel 1. And it's up to you to explain which one it is, state which one it is and explain why. Okay. The next question asks us to increase the input frequency until the output voltage becomes triangular, but not lower in amplitude. So in other words, this is kind of a square wave. As we increase the frequency, this will start to angle and get more and more triangular. At some point, it will become a triangle, and then its amplitude will start decreasing. You want to find that point where it just becomes a triangle. So what I'm going to do is start increasing the frequency of the input signal on the function generator. So I'm going to turn it up and see what happens. As I turn it up, you can see these are getting close together, as we expect from changing the frequency. As I'm increasing this, I may decide that I need to rescale what I'm seeing on the oscilloscope. Because all I'm doing is change the frequency, I'm going to simply increase or change the horizontal time scale. You can see that this is starting to become a little bit trapezoidal at the output. So it's starting to approach a triangle. So again, I just keep increasing the frequency and rescaling the oscilloscope as needed. I've currently hit the maximum frequency at the sort of hundreds of hertz range of 544 hertz. So I'm going to dial this down first and then increase my frequency range by one significant figure. So from the hundreds of hertz to the kilohertz range. As soon as I do that, you can see the output is beyond triangular. In fact, it's actually flat at the bottom. So I'm going to decrease my frequency a bit until I get to that point where it starts becoming triangular. You can see if I go lower, I get back that sort of trapezoidal shape. As I increase, I get a nice triangle peaking at the top here. And you notice it isn't balanced between the top and bottom. There is some asymmetry there. It's not a perfect triangular waveform. Depending on your experimental setup, the op-amp you're using, and how everything's connected, you may get something that is more or less triangular. So in this case, it's a matter of doing whatever is practical to get you to a reasonable looking waveform. Here we can then measure the period of the output voltage. So if I go to the measurement menu on the oscilloscope, I change my source to channel 2 because there's the output channel. And for the measurement type, you can see I can select the period. If we measure the period, it shows you with these dotted lines on the screen where it is measuring between to determine one period. And we can see that is measuring 927 microseconds from sort of middle of one triangle to the middle of the same triangle one period later. So that's measuring 927 microseconds. The final question here asks whether this is consistent, this period is consistent with the maximum slew rate of the op-amp. Remember, back in section 2.2, at the very start of the lab manual, the maximum slew rate of the op-amp was given as 23 volts per millisecond. When you answer this problem, make sure you understand quite clearly what the relationship between slew rate and period is. You may find it quite helpful to draw out a waveform and label these things on it. Okay, once we've done that, we then are told to readjust the frequency back to 100 hertz. Cool. So our frequency is now back at 100 hertz. I'm going to rescale the oscilloscope. And this time I'm going to use the autoscale function. And then we get back to the waveform we had before. What we're told to do now is to alter the switching threshold away from 0 volts by connecting an additional 10 kilo ohm resistor in parallel with one of the ones already in the circuit. So you can select add that in parallel with either the top 10 kilo ohm resistor or the bottom 10 kilo ohm resistor in this diagram, either one. That will change the threshold in one of two directions. We then want to calculate the new threshold voltage and measure it with a voltmeter. So I'm going to take one of these 10 kilo ohm resistors and I'm going to connect it in parallel with the resistor going between the non-inverting input and -5 volts. You could do it around the other way as well. It doesn't matter. So I put that into the circuit. And here's a good opportunity to talk about what happens if you're trying to make a connection in a circuit and your components or your wires simply don't reach. So you can see here, I have this extra resistor I'm adding off the side here, and it doesn't quite reach from where I need it to go to, which is the non-inverting input of the op-amp, to the negative 5 volt rail. And this is quite common. This happens quite a bit. What I can do instead is take the resistor from the negative 5 volt terminal out to a spare column in the breadboard somewhere, and then use a jumper to connect that to ground. So a jumper from that spare pin I'm using between that and, in this case, negative 5 volts, or wherever I want to connect it to. So if you run out of room or your components don't reach far enough, you can use jumpers to extend their reach. There's also a way to keep the breadboards nice and tidy as well. So if I connect that extra jumper in between negative 5 volts and the end of the resistor, you can see the output waveform has changed. You should be able to calculate what the new switching threshold will be. We then want to, using what we know about this waveform and the new switching threshold, calculate the proportion of time we expect the output voltage to be high. When we say high, we are meaning positive 5 volts in a sense. You'll often hear people talk about high and low voltages. That's often used in a digital voltage sense. Usually high is your largest positive voltage, low is your lowest negative voltage. So in this case, our high voltage will be plus 5 volts, our low voltage will be minus 5 volts. So this question asks to calculate the proportion of time you expect the output VO to be high based on your calculated threshold and your knowledge of the input waveform, which is a 4 volt peak to peak sine wave. We want to express this as a percentage, and you ask to show your working. Again, for these kind of problems, you'll probably find it useful to sketch a few waveforms and start labeling and annotating them. It's often a good way to get yourself thinking about what is actually happening and start setting up these kinds of problems. Okay. The last thing we're asked to do for this circuit is to measure the proportion of time the output is high. This is something we call the duty cycle. So when we think about a waveform that is going sort of high and low, or positive and negative, or positive and zero, or something like that, usually a square wave type thing like this, we often talk about the duty cycle. And that is the proportion of time the output is high. So that's essentially if it's high for 1 second and the wave period is 4 seconds, that is what we would call a 25% duty cycle, for example. We can measure that on the oscilloscope. I go to the measurement menu, channel 2, and I want to measure the duty cycle, which we've got here as an option. If I select that, I measure a duty cycle of 17.77%. You should be able to compare that to your calculation and see whether they match or not, and if they don't match, why they might not match. Okay, this brings us to the last circuit for this lab, which is the Schmitt trigger circuit. Again, I will disassemble this circuit here and then start setting up the Schmitt trigger circuit. Remember, when you disassemble your circuits or change things around, it's worth turning the power supply off, the outputs off, just to avoid any short circuit or accidental damage. Okay, so for this final circuit, we are creating a circuit called a Schmitt trigger. This is effectively a comparator with feedback. And we are going to have an AC input. So what we want to do is have two 10 kilo ohm resistors in the same setup we had in the last circuit. So between positive and negative 5 volts to provide a threshold to the non-inverting input. I'm going to reconnect those resistors now. Remember, on this package I was using the op-amp labeled B in this package. The non-inverting input was on pin 5 rather. So I reconnect those 10 kilo ohm resistors in. If you look at the circuit diagram, you'll see we also want a 100 kilo ohm resistor. And this resistor is going to be acting in feedback. That is, it is going from the output of the op-amp back to one of the inputs. The question at the very start of the circuit asks whether this type of feedback is positive or negative feedback, and asks you to explain your answer. So make sure you're comfortable with these ideas of feedback and what positive versus negative feedback is. So I'm going to take a 100 kilo ohm resistor, and I'm going to connect that between the output of the circuit, which for this circuit I got set up as pin 7 on this chip, and the non-inverting terminal. So that is pin 5. So I'm going to use this resistor to bridge pins 7 and 5 together. Finally, on our inverting terminal, we have our input sine wave as we had in the last circuit, going into the inverting terminal. So we get a final circuit that looks like this. And you can see that 100K feedback resistor across here. Now what we want to do is we want to, using what we know about Schmitt triggers, calculate the 2 thresholds that are generated by this feedback network. If you're not sure what that means, I suggest you consult your notes and either ask one of the TAs or ask in a tutorial or email one of the TAs to get a bit of clarity on that, because it is important you understand what a Schmitt trigger is and what it does. What I'm going to do now is I'm going to connect a couple of oscilloscope probes, one to the input and one to the output, same as we had in the last circuit, to show you what is happening in this circuit. So again, I'm going to use channel 1 as the input side. So measure what input is coming from the signal generator. And I'm going to use channel 2 to measure the output. So what is coming out of the Schmitt trigger. A quite common mistake that people make is when they are connecting up the grounds of their oscilloscope probes, they often accidentally connect the ground to the -5 volt rail rather than the ground rail. So just be careful of doing that. Okay, my oscilloscope probes are now connected. So now I'm going to turn the outputs of the power supply on. Okay, and now you'll see that for this sine wave, we again have a nice square wave output. You might think, well, what is the point of this? Well, if I were to have quite a noisy sine wave here, the Schmitt trigger would switch quite cleanly, whereas a comparator would start toggling like crazy. Again, consult your notes if you want to understand that a bit more. The very last question in this lab asks us to adjust the amplitude of the input sine wave. First down to 1.1 volt peak to peak, and then down to 0.6 volts peak to peak. As we do so, we want to observe the input and output waveforms. And the question asks us to explain why the relative phase of the 2 waveforms change as the input amplitude increases. So let me demonstrate what that is talking about. Remember, this yellow is on channel 1 is our input, and the green on channel 2 is our output. I'm going to just slightly scale the voltage so it's a bit easier to see. I'm also going to zoom in a bit in time as well. So take note of what this currently looks like. What I'm going to do now is to start to turn down the amplitude of the input signal. First to 1 volt, peak to peak. You can see this has gone a bit crazy as it's struggling to find a good signal. So I'm just going to auto scale, let it trigger nicely, and then rescale that time. And then I'm going to just gently decrease this down to 0.6 volts. As I do, keep an eye on these 2 waveforms and watch what happens. So now I'm going back and forth between 0.6, which is that here, and 1 volt, which is here. So you'll notice that as we expect, the amplitude of the input waveform decreases. That makes sense, that's what we're changing. But you'll also notice that the input waveform on the screen isn't moving side to side, but the output waveform drifts along to the left or right. Depending if I'm decreasing, it goes to the right. If I'm increasing, it goes to the left. This is the relative phase shift this question is asking about. So essentially, this question is asking why, when I change this amplitude, does this output waveform shift sideways? Why does it change phase relative to the input waveform? Again, you may find it useful to draw out some waveforms of the situation especially including those threshold voltages and input voltages, and see what looks as though it's happening to help with your explanation. There's all the experimental work for lab 2. Don't forget to finish off the calculations and theoretical discussions in the lab as well. Thank you.